In this lesson, let's look at how to solve absolute value inequalities. So I want to do this by kind of starting with an experiment instead of just throwing the rules out there at you, because I've noticed that a lot of students have trouble memorizing these rules. But I think if you take some time and try to understand what's happening here, the rules and the solutions will be easier to learn. So let's think about the absolute value of x is less than or equal to 2. I want to try to find where the solutions would be on a number line. So just by trial and error, let's plug all of these in and see which numbers should be graphed as part of our solution. So I'm going to start with negative 3. The absolute value of negative 3 is positive 3. And is positive 3 less than or equal to 2? No, it's not. So I won't graph the negative 3. Now let's plug in negative 2. The absolute value of negative 2 is positive 2. And positive 2 is less than or equal to positive 2. So I will graph the negative 2. Now let's plug in negative 1. Absolute value of negative 1 is positive 1. 1 is less than or equal to 2, so I graph that. Plug in 0. 0 is less than or equal to 2. Plug in 1. 1 is less than or equal to 2. Plug in 2. 2 is less than or equal to 2. But plug in 3 and it's broken again. So the only numbers I can find that will work are the numbers in between negative 2 and positive 2. And in fact, instead of just having those dots, I should graph the whole thing, because all of the decimals and fractions in between negative 2 and positive 2 would also be part of the solution. So now let's look at absolute value of x is greater than or equal to 2. And again, here's my number line. And I've got a few more numbers on it this time. So if we plug in negative 5, the absolute value of negative 5 is positive 5, and that is greater than 2. So graph that. Now let's plug in negative 3. Absolute value of negative 3 is positive 3. That should also be graphed. Now let's plug in negative 2. Absolute value of negative 2 is positive 2. That is greater than or equal to positive 2. Now plug in negative 1. The absolute value of negative 1 is positive 1, but that is not greater than 2. So I can't graph the negative 1. My graph seems to stop right here at negative 2. And now let's do the same thing with the rest of these numbers. If I plug in 0, 0 is not greater than 2. 1 is not greater than 2. But when I get to 2 again, the absolute value of 2 is greater than or equal to 2. If I plug in 3, that works. 4 is greater than 2. 5 is greater than 2. All of the numbers this direction are going to work. So my graph seems to be in two pieces. And because it's in two pieces, it's going to take two intervals to describe it when I get ready to write my interval notation. So now if you think about this interval over here, this looks like what we got when we worked on compound inequalities. And if you think about these intervals over here, we're going to have to write two inequalities to get two intervals, and we're going to join those inequalities by an OR. So this will be a compound inequality. With the less than problems, we'll get a compound inequality. With the greater than problems, we'll get two separate inequalities. So now let's take a look at a regular absolute value inequality. Let's solve absolute value of x minus 4 is less than 3. Now this is a less than problem, so this should be written in compound inequality form. And what we do is we take whatever's in the bars and we put less than signs on both ends, and what's in the bars is stuck between negative 3 and positive 3. So whenever you see a less than, you put less than signs on both ends and you put negative number, positive number. Now, that assuming that you have a positive number here to begin with, because if you don't, then you got another problem. But we won't talk about that right now. Now let's solve this. So we'll add 4 to each piece. And negative 3 plus 4 is 1. And on the right side, 3 plus 4 is 7. So we find that x has to be stuck between 1 and 7. There's our set builder notation. Now, if I shade the numbers between 1 and 7 and use parentheses for both of them, then I can see that my interval should be from 1 to 7. And now let's do a greater than problem together. So this is a greater than problem. And so instead of writing a compound inequality, we can't really do that, because since this graphs both ends of the line, we can't require x to do two things at once. It can either do the left end or the right end, but it can't do both at the same time. So when I write my two inequalities, I'll simply write the first one is just exactly the same as the problem, but without the bars. Now the second one, I flip the symbol over and I flip the sign of this number on the right side. So look at it one more time. I say what's in the bars is greater than 7. In other words, I copy the problem over but without the bars. And for the other one, I copy the left side over, but then I flip the symbol over and I flip the sign of this number. And that gets us two ends of the line, two ends of the graph. So here we go. We're going to solve the first little inequality. Let's subtract 5 from both sides. And that will give us negative 2x is greater than 2. Now divide both sides by 2, or sorry, negative 2 actually. And when you do that, it's going to force you to flip your symbol over, and we'll have x less than negative 1. For the second inequality, we'll subtract 5 from both sides, and we'll have negative 2x is less than negative 12. Divide both sides by negative 2, and that's going to force you to flip your symbol over, and you'll have x is greater than 6. So now I will have one end of the line graphed here and another graphed here. I went ahead and did my set notation. Your set builder notation will just be these two inequalities with the word or in between them. And here's your graph. And remember that this is a greater than problem, so it graphs the two ends. So x is less than negative 1 will be to the left. X is greater than 6 will be to the right. And we'll have our parentheses here. And because the graph is in two pieces, it takes two intervals to describe it. So the first one is from negative infinity to negative 1, and then from 6 to infinity. And notice the little union symbol in here. The union symbol is not the U on your keyboard, but it is just it's actually called a cup or a union symbol. It's just a U, but doesn't have the tail on it. So if you're working in my math lab, you need to actually look for the union symbol button over on the toolbar, but do not use the U on your keyboard. Okay, here's another one. And notice it is a less than problem. So with less than problems, we copy what's inside the bars, we put less thans on both ends, and we put the positive and negative of this number on both ends. So negative 2 is less than 2x plus 6 over 3, which is less than 2. Now you know if this were an equation, you'd just multiply everything by 3. So let's do that to clear out that denominator. And that will get us negative 6 is less than 2x plus 6, which is less than positive 6. And then we will subtract 6 from each part. And that will get us negative 12 is less than 2x, which is less than 0. Divide everything by 2. and that will tell us that negative 6 is less than x, which is less than 0. Of course, our set builder notation looks exactly like this, and our graph is in between negative 6 and 0 with parentheses, and then our interval notation is from negative 6 to 0 with parentheses. Okay, one more. Let's do 3x minus 3 over 4 is greater than or equal to 6. So this being a greater than problem, we'll write two inequalities. One inequality that's the same but without the bars, the other one that's the same on the left side, but we'll flip the symbol and flip the sign of the right side. Okay, now to solve the first one, we multiply both sides by 4. That will give us 3x minus 3 is greater than or equal to 24. We'll add 3 to both sides. That gives us 3x is greater than or equal to 27. Divide both sides by 3. X is greater than or equal to 9. Now for the other inequality, again, same steps. We'll have 3x minus 3 is less than or equal to negative 24. Add 3 to both sides. 3x is less than or equal to negative 21. Divide both sides by 3. X is less than or equal to negative 7. So these are our two inequalities. Now notice that x cannot do, there's no number that can do both at the same time. So what we're saying here is that any number that fulfills either requirement is part of the solution. So anything x is greater than 9 or anything where x is less than or equal to negative 7 will be part of the solution. I mean, if you think about it, you can't find a number that would do both. And that's why you cannot write this in compound inequality form, because if you write it in compound form, you're saying that x has to do both. You can find numbers that are greater than 9. You can find numbers that are less than negative 7. But you can't find a number that does both. So, alright. Now here's our number line. We know that with greater than problems we always graph the ends. So I have or equal to bars on my symbols, so let's use brackets here. And then the left interval is from negative infinity to negative 7. And the right interval is from 9 to infinity. And again we have the union symbol in between them. And that's it. Okay, so to recap, on less than problems, you're going to write a compound inequality. That's one interval in between two numbers. And on absolute value greater than problems, you're going to write two inequalities with the word or in between them. Your answer is going to come in two intervals. And now, caution, I never want you to write greater than problems in compound form, because, for example, if we had absolute value of x is greater than 5, if you write it in compound form, it looks like this. But you can't find an x that is both greater than 5 and less than negative 5 at the same time. And that's what that says. So I know sometimes people, they want to write it this way because it's convenient, and when you get to the end you just know that you're going to graph the two ends of the line. But I'm telling you that's not a good idea because it's misleading. It doesn't say what you think it says. You may know how to read it, but somebody else wouldn't. It's like if you misspell a word. You know what it means, but somebody else who reads it might not. So it's best just to learn how to write it correctly in the first place. So, you must write greater than problems in two inequalities. And that's about all I have to say there.